Assalamu alaikum. Welcome to the new lecture. In the last lecture, we concluded that uh, in case of the efficiency of the transmission line with this transformer, that the maximum efficiency occurs when the variable losses, that the copper losses, are equal to the constant core losses. In that case, the efficiency of the transformer will be maximum. That means the efficiency is maximum at a load when the copper losses are equal to the core losses. So this equation can be written like this, that's I2 square R equivalent to, that is the secondary side will be equal to Pi. Pi is the core loss. So when we divide both sides by I2 square, sorry, R equivalent, I2 square will be equal to Pi divided by R equivalent square. So again divide both sides by I2 FL square. So this will be I2 square, I2 by FL whole square, that is equal to Pi divided by I2 square FL R equivalent to, let us call it, let us equate it to some K square, a constant K. Now this value, that is the full load current flowing, square of the full load current multiplied by R equivalent, will give us the copper loss at full load, that is PC full. So when you equate these two equations, that's Pi divided by this, so that means K will be equal to square root of iron losses divided by the copper losses. So when you equate these two equations, that means K is equal to I2 divided by I2FL. So here this PCFL is the full load copper loss, because this is the full load current flowing through these resistances. So this parameter K is very important in this case. So what is this K? Thus the efficiency is maximum at a fractional load current given by the above equation, that is this. Fractional load current will be I2 by IFL. So maximum efficiency will occur at K, where K is equal to I2 by IFL, or K is equal to Pi divided by PC full square root. Now multiplying the numerator and denominator of the above equation by V2, that is this equation, we have to multiply and V2 to denominator and the numerator. So it comes out to V2I2 divided by V2I2FL. So you can multiply, cross multiply it, that means K into V2I2FL will be equal to V2I2. That means the rating of the transformer at which the maximum efficiency occurs will be some fraction of the actual, that is the rating of the transformer. So we can say V2I2 will be equal to K times S2. That means the maximum efficiency occurs at a load that is equal to K times V2I2FL, or K times S2, where S2 is the VA or KVA of the KVA rating of the transformer. S2 means here, since we have referred it to secondary, that means S2 will be here, voltage and currents will be of the secondary side. So where we can say K is the fractional current of the full load current at which the maximum efficiency occurs, or K is the fractional load of the actual rating of the transformer at which the maximum efficiency occurs. That is one and the same thing. So the expression for the maximum efficiency is given by theta max will be equal to K times S2, where V2 into I2 is equal to S2 cos of theta 2 divided by K times S2 cos of theta 2, where this is the P naught. Theta 2 is the power factor of the load plus twice Pi. That means theta max will be equal in terms of voltage and current, K times V2I2 cos of theta 2, K times V2I2 cos of theta 2 plus twice Pi. It can easily be observed from the above equation that theta max increases with increase in power factor. Maximum efficiency increase with increase in power factor, and definitely will be maximum or highest for the unity power factor. Also theta max will be 0 and cos theta 2 is equal to 0. That means for reactive power, this maximum efficiency will be 0. Even efficiency will also be equal to 0, normal efficiency for reactive load. Therefore, knowledge of transformer losses is an important as its efficiency. So efficiency as well as losses are very important. So power transformers use a bulk power transmission are operated near about full load at all the times. The power transformers, which are very huge in structure, they are usually operated at the full load. So they are designed to have the maximum efficiency at the full load. So this is very important, and I will tell you how this is done, how this design is done. So you just have to keep in mind that maximum efficiency for the power transformers is kept at the full load. On the other hand, the distribution transformer supply load which varies over the day through a wide range. We cannot say that all the time the distribution transformer is loaded equally. The load will change as per the requirement. Such transformers are therefore designed to have maximum efficiency, roughly about 3/4 of the full load. That means at the 70 to 75%. So in case of power transformer, maximum efficiency is kept at the full load, whereas in case of distribution transformer, maximum efficiency is kept at the 3/4 or you can say 70 to 75% of the full load. Normally, transformer efficiency is maximum when the load power factor is unity. That we have already seen from here, because when cos theta reduces, this also will reduce. From figure shown below, that is this figure, it is seen maximum efficiency occurs at the same load current independent of the power factor. That is at this point. You can see all the curves. Power factor is 1, power factor is 0.8, power factor is 0.6. Maximum efficiency occurs roughly at this point. It's independent of the power factor. It does not change with the power factor. Because the total core losses PC and the equivalent resistance R equivalent are not affected by the load power factor. So these two will not be affected by the load power factor, because you can see that this K uh, this K, that is the value of the current at which the maximum power factor, maximum efficiency occurs, is dependent upon PI and PCU full. They are constant. This copper losses are variable, but full load copper losses are constant because they depend upon the resistance and full load current. Both are constant. The reduction in the load power factor reduces the transformer output, and transformer efficiency will also reduce. That's quite obvious from the graph as well. So one more thing that you need to understand, that when load is zero, that when I2 is zero, that is depicted in this efficiency, that is maximum efficiency as well as normal efficiency will also be zero. So that way also. Now we can say that we can have one more explanation on this graph. When load current is very small, you will see that output is very small, but the losses, that the constant core losses are very large. It is because of the constant core losses, the efficiency is very small. As load current increases, the power increases, but I square R also increases. And at a point when the this I square R losses are equal to the constant PI losses, so at that time you will see the efficiency will be maximum for all these power factors. But after that, again, when current increases beyond this point, when the maximum efficiency occurs, you will see the droop in the efficiency curve. It is because then the dominant factor will be I square R. I square R would have been more as compared to PI, and efficiency again decreases. So it will be maximum when the constant losses are equal to the variable losses. So the next point is the all-day efficiency. The all-day efficiency of a transformer is the ratio of total energy output kilowatt hour in 24-hour day. That's why it is known all-day efficiency, to the total energy input in the same time, that is in one day. So actually, normal efficiency is the efficiency that uh, we define in terms of power, but all-day efficiency is the efficiency we define in terms of energy in one day. So since the core losses are constant independent of the load, the all-day efficiency of a transformer is dependent upon the load cycle. That means how much time the load will be, how much time the load will be on or off. But no prediction can be made on the basis of load factor, that is average load by load. Peak load is known as load factor because it will show you actually the average of the overall load. It is an important figure of merit for distribution transformer which feeds daily load cycle varying over a wide load range. Higher energy efficiencies are achieved by designing distribution transformer to yield maximum efficiency at less than full load, that we have already discussed, usually around 70 to 75% of the full load. So that is why they are to be designed like that, because they are not always operated at the full load. This is achieved by restricting the core flux density to lower values by using relatively larger core cross-sectional area. It means larger iron to copper weight ratio. I'll discuss this in terms of this key. So in case of distribution transformer, because since it will be always supplied. The primary side will always be supplied. Load may vary. This constant losses will be more as compared to the variable losses, we can say, because it will be always there will be a time when the load output load will be less uh, as compared to the full load. So we can say we have to supply always the core losses. So to reduce the core losses, or we can say to reduce the efficiency, maximum efficiency to the 70% of the full load, you will see that we have to reduce this pi, that the core losses. So how to reduce this? We have to decrease the flux density. Sorry, we have to increase the flux, reduce the flux density, because this pi are proportional to this flux density. So by reducing the flux density means we are increasing the area of the cross-sectional area of the core. When we increase the cross-sectional area of the core, we have to use more core, that is more iron. So this can also be done by increasing the value of this power. So when we increase the value of this power, we have to reduce the resistance of the winding. That means reducing the resistance of the winding means reducing the amount of copper. So that means we are using less copper, more iron. That is, it means larger iron to copper weight ratio. In case of power transformer, reverse will happen. We have to make this K equal to the, we can say quite close to the one, that's full load. In that case, Pi should be larger. This PC should be smaller. Pi larger means we have to use flux density higher. To increase the flux density for same voltage and same frequency, we have to decrease the cross-sectional area of the iron. That means low core or low amount of iron weight is used. To decrease this, we have to increase the cross-section area of the copper windings, because in that case resistance of the winding will decrease. So we have to use more copper. That means in this case, for power transformer, we have to use low iron to copper weight ratio. But for distribution, it has larger iron to copper weight ratio. Now let us try to do some numericals. Okay, the following data were obtained at a 20 kV 50 Hz to 2200 distribution transformer. Draw the approximate equivalent circuit of the transformer. Okay, this is actually the old problem. So using the same data of the problem, we have actually this problem that we have to do. For the transformer example 3.7, that is this one. Calculate the efficiency. The low voltage side is loaded fully at 0.8 power factor. So low voltage is fully, that means low voltage side we have a 200 volt rated voltage, and what will be the rated current on the low voltage side? So it is 20 kV divided by 2000, it will be 100 amperes. Okay, so it is 100 amperes. So the power output will be equal to V2I2 cos of theta. So output power is given from the question. So the power output will be 16,000 watt, independent of lag only. That will be definitely the case. Now total power loss will be PL, PI plus PC. What is PI? PI is the open circuit power, that is 120. PC is the short circuit power, that is 300. That is 420 watts. So efficiency will be equal to simply uh, output divided by output plus losses, or 1 minus PL, that is losses divided by output plus losses. So it comes out to be 97.44%. For maximum efficiency, the fraction of the load can be calculated as the square root of PI by PC, that is 120 by 300, that is 0.632. So this will be the fraction of the load at which maximum efficiency occurs. So that is 0.83 per unit load, that is the independent load factor. Now Neta max at cos theta 2 is equal to this 0.8, that means V2 I2 cos of theta will again be this 16,000, but it has to be multiplied by this k times. So you can use that k times V2 I2 cos of theta divided by k times V2 I2 cos of theta plus 2 times Pi. This will be the same formula. So it comes out to be 97.68%. It will be the maximum efficiency of the above transformer. Now the second one, here a 500 kVA transformer has an efficiency of 0.95 at full load and also at 60% of the full load, both at unit power factor. For example, this actually uh, derived from this. For example, if you draw a line from this to this, you can see, let us say this is 0.95 or 0.98. This is 60% of the load. This is how much full load. So that's why we have the two values of same efficiency, because it started from lower value and goes to the maximum value and then comes again to the lower value. You can see overhead. So for this case, at the full load, we know that neta maximum, both are at the unity power factor. That means the efficiency that is given as 0.95 is equal to 500 into cos of theta, that's 1, 500 into cos of theta, plus pi plus pc. So in this case, these two are variables which are not known. We need to find out them. So this is one equation that is used to calculate this one equation. That means you can see it, pi plus PC will be equal to 500 divided by 0.95 minus 500. So you can use that for one equation. Also, at 0.9, sorry, at 60%, it has the same efficiency. That is, efficiency will be 0.95, 500 into 0.6, because 0.6 into full load, 60% of full load will be 0.6 into 500. So output will be 500 into 0.6, PI will be as it is, but PC will change as per the as per the load, because you know that when full load is 0.6, full load is 0.6, that means at unity power factor, so that means V2 I2 of this will be equal to 0.5, 0.6 of the V2 I2 full. V2 and V2 remain always constant. That means this will be equal to 0. This I2, which is now at 60%, will be equal to 0.6 into I2 FL. So this PC is actually the value which we calculate at the full load. That is full load copper losses, and 0.6 will be then, because now the current will be 0.6 of the IFL, so it comes out to be 0.6 square IFL square into R equivalent. So it will be equal to 0.6 square into this PC full load current. So it will be always like this. So when you solve these two equations, PI will be equal to 9.87 kilowatt and PC will be equal to 16.45 kilowatt. Now we have separated the losses, we have calculated the losses. Now determine the efficiency of the transformer at 3/4 of the full load. So we know that PI, we know that PC. Now full load is given as this. Now it is telling us to calculate this at the 3/4 of the full load, that is 0.75. That means 500 into 0.75 divided by 500 into 0.75 plus, it will remain as it is. It will remain as, but it will be multiplied by this. It is exactly the same manner that we have done for the 60% of the load. This is 75% of the load. So same unit will be multiplied to this, and it will be equal to 0.75 square into 16.45. It will be equal to 95.14. This will be its efficiency. You can also calculate its maximum efficiency. That will be equal to K times this full load. There will be K times full load plus 2 times PI, that is this. But K is equal to square root of this divided by this. You can also calculate that one. And you will see that that will be definitely greater than this 95, because it is at 60%, it has 95%. At full load, it is 95%. It means from 62, it is coming down. There will be some percentage will be definitely greater than 95%. Now, one numerical is the all-day efficiency. Here, we need to be very careful. We have to calculate the energies all the time. A transformer has its maximum efficiency of 0.98 at 15 kVA at unit power factor. Okay, so compute its all-day efficiencies for the following load cycles. Here, a full load of 20 kVA. That means its full load is 20 kVA. It is rated for 20 kVA. So that you need to actually identify from this part A. It should have been usually given it's a 20 kVA transformer. That means it's rated, but it is here given, so you need to identify here. So it is full load 20 kVA, 12 hours per day, and no load for the rest of the day. That means for the other 12 hours it will be on no load. So the other cycle, it has full load for 4 hours and 0.4 full load for rest of the day. Assume that the load is to operate on unity power factor all day. So for the simplicity, it asks us that it is always operating at unity power factor. So we know that neta max is equal to this P naught divided by P naught plus twice P. Actually, this from this sentence, from this to this, we need to calculate it is Pi, because for maximum efficiency there will be only Pi there. So P naught is how much? P naught is 15. It is given at 15 kV at unity power factor. It will be 15 into 1 is 15 divided by 15 plus twice Pi. It is given to be equal to 0.98. So when 0.9 is equal to 15 divided by 15 plus twice Pi. So Pi has been calculated to be equal to 0.153 kilowatt. Okay. So the fraction of the load that is given usually at which the maximum efficiency occurs, that is K into ratings of the term, that's Ks, that is already given as 15. That means Ks is equal to 15 where S is also given as 20. That means K will be equal to 15 divided by 20, and K is 15 divided by 20. K square is equal to Pi divided by Pc, where K is 15 divided by 20. That is 15 divided by 20 square is equal to Pi, which we have calculated just now. So here we can calculate the value of Pc. Pc comes out to be 0.272 kilowatt. So we calculated the core losses as well as copper losses. Now we'll divide the time zone for 12 hours and 12 hours. For first 12 hours, the power consumption and the output is 20 watts, and the total energy for this period will be 20 watts into 12. It will be 240 kilowatt hour. You have 240 units of energy. So input power will be simply equal to this power plus the losses. That is this power, energy. This power plus the losses, 20 plus this power, that's a constant power, and this power, that is the full load copper losses. And since full load is taken during this time interval, it will be remain as it is. So total power will be equal to 20.45425. So during this period the energy will be, that is multiplied by 12, it will be equal to 245.1. Similarly for this period you will see that this power output is 0, Pi will be this much, and there will be no Pc because there is no load on the secondary side of the transformer. So it will be only um, copper losses. So for 12 hours it will be equal to, multiplied by 12, it will be 1.8. Total input power will be, total input energy will be 246.9. So all day efficiency will be equal to output energy divided by input energy, that's 240 divided by 246.9, that is 97.2%. Similarly for case B, so full load is operating for 4 hours and 0.4 of the full load, that means 0.4 into 20 will be equal to 8 kilowatts for 20 hours. So for this case the energy will be 20 into 4, that is 80 kilowatt hour, but for this case it is 160 kilowatt hour. Okay, the total output power will be 240 kilowatt hour again. P in will be equal to 240 plus Pi plus Pc. So 240, sorry, P naught is 20, it is 0.153, it is 0.27, it is 20.425. It will be again the same. So multiplied by 4, that is now time is 4, it will be 81.7. Now for this case you can see this is P naught is 8, Pi is constant, it is 0.1. But since this is the full load copper losses, we need to convert them, we need to calculate the copper losses at which the load is 8 kilowatts. So it will be a fraction of that, as 8 divided by 20 whole square, or which is given as 0.4 of the full load. 0.4 square, 0.4 square into 0.272, that is equal to 8.196. And for 20 hours it comes out to be this. When you add them up, it comes out to be 163.9 kilowatt hours. Total will be 245.6 kilowatt hours. So the efficiency for this case will be equal to 40 divided by 245.6, that will be 97.7%. This is how we can calculate the all day efficiency. All day efficiency and normal efficiency are only different, that all day efficiency is calculated in terms of energy and efficiency is calculated in terms of power. Now voltage regulation, we come to the another parameter of the transformer, important parameter of the transformer, that is the voltage regulation. Constant voltage is a requirement of most domestic, commercial and industrial loads. Almost all we can say all the equipments in the power system, they need to have a constant voltage. It is therefore necessary that the output of the voltage transformer must stay within the narrow limits. We can say the transformer should give always the constant voltage, but it's not possible that it will always give us the voltage at a constant value. But sometimes we can allow some variation of this, but that variation should be within the narrow limits. As I told you in the lab, that should be plus minus 5%, which is the normal limit of the voltage in India, because this voltage will vary as load and power factor will vary, because this voltage is dependent upon the load as well as on the power factor. This requirement is more important in distribution transformer as these directly feed the load centers. Even if there is some voltage variation in the power transformer, there is no problem because they are far away from the load center. They do not feed directly to the load. But in case of distribution transformers, this has to be kept in mind while designing the distribution transformer, that the voltage variation of the transformer should remain within the narrow limits. The voltage drop in a transformer on a load is chiefly determined by the leakage reactance, as we have already discussed it, which must be kept as low as design and manufacture technique would permit. We need to keep them as low as possible. We cannot eliminate it, that is obvious, but we need to keep them very small. The figure of merit which determines this voltage drop characteristic of a transformer is known as voltage regulation. The voltage regulation is defined as the change in magnitude of the secondary terminal voltage. This is important, it is only related to magnitude, not to the angle or the phasor, which when a full load rated load of the specified power factor supplied at rated voltage is thrown off. That is reduced to the no load with primary voltage and frequency held constant as a percentage of the rated terminal voltage. In terms of symbol, it is known as V2 naught. That means the no load voltage at the secondary terminals, and then there is no load minus the full load voltage divided by the full load voltage into 100. So rated secondary voltage while supplying the full load at specified power factor, V2 naught will be the secondary voltage when load is thrown off. So this is what is meant by the voltage regulation. So, or in other words, we can say that the voltage regulation is the difference of, or we can say change in the voltage from no load to full load when load changes, from no load to full load as and expressed as the full load voltage of the transformer. So this figure A shows the transformer equivalent circuit referred to the secondary side, and figure B gives its phasor diagram. This is very simple. Let us assume a lagging current here. This is V2, first the reference, that is the secondary voltage. This is the lagging current. So then this voltage will be equal to V2 plus IR plus J IX. So this type of phasor diagram I have shown you in the class as well, because this will be using quite a time or quite often. So then we need to add resistive voltage drop and reactive voltage drop to V2 to get V1. So resistive voltage drop will be in phase with I. So this will be in phase with I. This will I into R. And reactive voltage drop will be perpendicular and leading to this current by 90 degree. It will be like this. You can see there is a 90-degree phase shift, and it should be anti-clockwise leading to this. So this will be like this. So O and A, when you connect them, so this will give us the V1. So from this diagram, we make some assumptions that usually when you calculate the voltage regulation, you need to calculate this value. You can calculate it simply by adding the phasors to this voltage. That is, one phasor will be I into J, I into X plus I into R. You get the V1. So, but here we'll derive an approximate formula for voltage regulation. The approximation will be the delta should be very small. When delta is very small, you will see that this V1 will be quite close to this OE. So that's why we have assumed that V1 will be quite close to OE. So voltage regulation will be defined as this V1, because when you open circuit there will be no current. This V2 will be equal to V1 because there will be no voltage drop here when there is no current. So we can say voltage regulation for this case will be equal to V1, magnitude of V1 minus magnitude of V2 divided by the V2. So here we need to find out these values. So V1 minus V2 divided by V2. V1 we have assumed to be equal to OE. That means it will be OE, that is V1, minus OB, that is V2 divided by V2. Or we can say we have this OE minus OB will be equal to BE divided by OB. Or we can say BE divided by V2. So we need to calculate first BE. From this diagram you can see BE will be equal to BC plus C. This BC will nothing but the cos component of this voltage phase I into R. That means BC will be equal to IR cos of theta or IR cos of phi. Okay, that is what I have written over here. BC is equal to IR cos of phi. Now If this is theta, this angle will be 90 minus theta because this angle is 90. This angle will also be 90 minus theta. This angle is 90. That means this angle is same again, theta. That means here we have used phi, it will be phi. So this value, that is this value will be same as this value, that is CE. So we can calculate this value. This will be nothing but the sine component of this Ix. That means this value CE will be equal to Ix sine of phi. So this BE will be equal to this IR cos of phi plus Ix sine of phi. So that means V1 minus V2, which is approximately equal to BE, will be equal to IR cos of phi plus IR sine of phi for lagging. And for leading also, you will see that this will be equal to this value. So I think I will stop over here. We will continue in the next class. Thank you.